We now develop the algorithm from the invariant and the theorem. The algorithm will be a loop with initialization. Each iteration of the loop will place one more node into the settled set. The first loopy question is, what should be done to truthify the invariant? Stop the video and figure this out for yourself, then continue. Here's what we do. Fix the frontier set to contain only start node v and set d sub v to 0. Now P2 is true. Make the settled set empty. That makes P1 true. P3 is also true since the settled set is empty. We now write the loop, and the second loopy question has to do with the loop condition. When can the loop stop? That is, when do all elements of array D have their final values? Stop the video and figure this out. Then continue. By P1, upon termination, all reachable nodes should be in the settled set. By P2 and P3, this will be the case when the frontier is empty. For if the frontier is empty, V is in the settled set. Since the frontier is empty, no edge leaves the settled set. So any node reachable from V is in the settled set. Thus, the loop stops when the frontier is empty and continues when the frontier is not empty. You might have chosen the loop condition, the settled set doesn't contain all nodes reachable from V. This condition may be much harder to implement than the one we chose, because it may be difficult to determine the number of reachable nodes. But the condition, the frontier is not empty, is easy to check. Further, if the frontier set is empty, the number of reachable nodes is indeed the size of the settled set. Third loopy question. How does a repetend make progress toward termination? Stop the video and figure this out for yourself, then continue the video. The repetend should increase the size of the settled set, since the loop terminates when the settled set contains all nodes reachable from V. The theorem shows us how to make the settled set bigger. Let F be a node in the frontier with minimum D value. The theorem says that D sub F is the shortest path distance from V to F. So, move F from the frontier to the settled set. This keeps invariant P1 true. We show this happening. We also show that there may be edges leaving F and going to nodes in all three sets. We'll have to deal with these to maintain invariance P2 and P3. And we also show the shortest path from V to F. Loopy question 4. How is the invariant maintained? P2 may be false because there may be a path from V to F to a node like W2, with all but W2 in the settled set, and it may have a shorter distance than D sub W. P3 may be false because there may be an edge from the settled to the far off set, like node W0. Stop the video and think about how to truthify P2 and P3. Don't be discouraged if you don't get it right. This is a lot harder to answer than the other three questions. Then continue the video. We use a loop that processes all edges leaving F, that is, all edges F, W for some node W. There are two cases to consider. First, W is in the far off set, and second, W is in the settled or frontier sets. So we have an if statement. If W is in the far off set, like W0, set D sub W to D sub F plus the weight of the edge from F to W, and then put W into the frontier set. After this is done for all edges FW with W in the far off set, P3 is true. Let's remove node W0 from the picture. Case 2. If W is in the settled or frontier sets, like nodes W1 and W2, a new path from V to F to W has been created with all settled nodes except perhaps for the last one. If its distance, d sub F plus the weight of the edge from F to W, is less than d sub W, a shorter path has been found. So change d sub W accordingly. Note that if W is in the settled set, like W1, nothing will change. After all edges leaving F are thus processed, invariants P1, P2, and P3 are true. This completes the development of the algorithm.